Hello. So far, we found out how to compute different cosmological models. But what good are they? The basic goal of cosmology is to figure out in what model universe do we live. And you will recall that they are basically distinguished by their history with expansion rate. How does the scale factor changes as a function of time? If we can figure out which curve of those we live on, we'll know about cosmological parameters. The expansion factor, R of t, is simply related to redshift. That is an observable quantity, and that's an easy part. The other axis is the time axis. Now, unfortunately, distant galaxies do not carry gigantic clocks on them, so it's very hard to figure out what is the look-back time between us and some distant point in a way that can be measured. So instead of that, what we do is we transform coordinates. Instead of the look-back time, we can use distance, which is simply time multiplied by the speed of light. And distances, in principle, we can measure. So we flip this diagram, and instead of expansion factor R of t, we use the redshift, which is an observable quantity. And instead of the time, we use a distance, which we can figure out how to measure in some way. So essentially, all cosmological tests boil down to this. We have to somehow measure a set of distances to points as a function of redshift. And because the whole thing just scales with Hubble constant, we only need to determine the shape of that curve. So let's figure out how to measure distances in cosmology. A convenient unit of the distance is Hubble distance, which is simply speed of the light divided by the Hubble constant. Recall that Hubble constant has dimensions of 1 over time. And obviously 1 over Hubble constant is called Hubble time. In the units of Hubble constant of 70 kilometers per second per megaparsec, which is close to its actual measured value, Hubble length is about 4.3 gigaparsecs, and Hubble time is a little shy of 14 billion years, which is actually pretty close to the actual age of the universe. Now, at low redshifts, the expansion is linear. Hubble's law applies, and the distance is simply redshift times the Hubble distance. But the further out we go, the relativistic effects come into play, and things are a little more complicated. Generally speaking, we can compute the co-moving distance in coordinates that do expand with the expanding space, as follows. We can integrate the element of redshift divided by the function, which is really Hubble constant at that given time, and which is given here. You may actually remember a similar expression inside the Friedmann equation. You see three terms. The density of matter multiplied by the cube of 1 plus redshift. Well, that's probably because density of the matter scales as the cube of the expansion. Then there is a curvature term, and there is a constant term, which corresponds to a cosmological constant. There is actually one more term missing, which is the relativistic matter, which would be omega of radiation times 1 plus redshift to the 4th power. But that's only important in the early universe, so it's generally neglected in this computation. Now, the really useful quantity in computing physical parameters is not co-moving distance per se, but a quantity that is adjusted for the curvature of the space, which is called the transverse co-moving distance. And the formula for that is given here. In the case of a flat universe, those are the same. In the case of positively or negatively curved ones, there is a correction. Now, remember, omega curvature, so-called curvature density, does not really correspond to density of anything. It is just a quantity that makes the sum of all densities equal to 1, always. So omega curvature is really 1 minus the omega of matter, omega radiation, and omega of cosmological constant. So how can we derive this? We'll start with Robertson-Walker metric, the basis of all relativistic cosmological models. Since only the radial coordinate matters, by and large, we can then simplify that, get rid of both the angular terms, and just have the radial term. So we'll take square root of both sides and integrate. Generally speaking, this integral cannot be solved analytically. It has to be solved numerically. In some special cases, such as when the density of the vacuum, of cosmological constant, is equal to 0, there are analytical solutions. In that case, the formula for the distance is shown here. It's expressed in the older units of q naught, which remember is deceleration parameter, and in the absence of cosmological constant, it is equal to the density parameter divided by 2. Now, for a universe with non-zero cosmological constant, things are a little more complicated, and generally speaking, the integral has to be computed numerically. So here is a plot of distances for several different cosmological models expressed in units of the Hubble distance as a function of redshift. It's in units of Hubble distance because the whole thing scales directly, linearly, proportionally to Hubble constant. And we can separate measurement of the scale of the universe through Hubble constant and the shape of the universe, if you will, which is the other cosmological parameters. But how do we relate this to the things that are actually measured? We can measure, roughly speaking, two kinds of things: brightness of some source far away or its angular size. In cases where we can use brightness, you can imagine using source of a standard luminosity, so-called standard candle, viewed at different distances, and using the relativistic version of inverse square law to find out how far it is. So in simple Euclidean non-relativistic universe, the flux would be luminosity divided by the area of the sphere with the radius from here to there. In the case of an expanding universe, there are two terms of 1 plus redshift that come into play. One of them accounts for the energy loss of photons because their wavelengths are stretched as 1 plus redshift. But the thing is moving far away from us and fast, and so we have to account for the relativistic time dilation. The clock ticks slower there by a factor of 1 plus z from our point of view, and so the rate of the photon emission is affected by exactly the same factor. So we have 1 plus z squared in the denominator. In other words, in an expanding relativistic universe, objects appear dimmer than they would if the universe wasn't expanding. So for convenience, luminosity distance is defined as the actual radial distance times 1 plus z. So when you take square of it, you recover the familiar inverse square formula. That is if we can measure the total luminosity, but we usually measure specific flux, which is power per unit wavelength or unit frequency. In that case, we recover 1 power of 1 plus z because the angstroms are stretched by exactly the same factor, or the hertz are also stretched by 1 of that factor. So in case of specific fluxes, there are no 2 powers of 1 plus z, the only 1. So here is a plot of luminosity distance in several cosmological models, again expressed in units of Hubble length as a function of redshift. You can see the typical redshifts of interest in modern cosmology. It's of the order of 10 Hubble lengths. The other kind of thing that we can measure is the angular size of things. Imagine if you had standard gigantic ruler that you can view at different redshifts from us. Then its angular diameter will tell us how far we are for a given cosmology. In a simple Euclidean non-expanding space, that angle will be the size of the ruler divided by the distance. That is as far as co-moving coordinates are concerned. But what if the object is fixed in proper coordinates, say like a galaxy? Galaxies do not expand with expanding space. At any given redshift, proper size is larger than the co-moving size because co-moving coordinates have expanded since then, and it's larger by exactly power of 1 plus z. So here we have the opposite scenario. The objects in an expanding universe are actually bigger than they would be in a non-expanding case. And we divide the distance by 1 plus z so that we can use the familiar formula, and that's called the angular diameter distance. Here is a plot of angular diameter distance as a function of redshift for several popular cosmological models. You will notice that in many of them, there is a maximum. At some distance from us, things no longer appear smaller. This is specific to relativistic cosmology. In a Euclidean space, the further away something is, the smaller it's going to look, always. Here, past certain depth, things actually start getting larger again. Finally, we can imagine measuring volumes out to some redshift. If, say, universe was populated by particles such as galaxies or Lyman alpha clouds, and we can count them, then their number per unit volume is something that will be also dependent on the expansion rate. So the volume element, its increment, radial increment as a function of redshift, is given by this formula. Generally speaking, that has to be always evaluated numerically. And the total volume integrated from here to some redshift of z is given by these formulas. So here are plots of the volume element as a function of redshift for several models. As you can see, those curves can differ very substantially at high redshifts. And that's why this is potentially an interesting cosmological test. Here, as well as in the other plots, all of the curves are really close together at very low redshifts when things are asymptotically Euclidean. So that's the distances. What about the look-back time? Whereas we cannot directly measure it as a function of redshift, it is a useful quantity when considering things like galaxy evolution. The time elapsed since some redshift of z, which is the look-back time, is given by the same formula as we've seen before, except corrected by 1 plus z. So then again, this also has to be evaluated numerically, except for some special cases like with zero cosmological constant, when analytical solution does exist. If we're to integrate this all the way out to infinite redshift, that is to the Big Bang, we will get the total age of the universe. So here is the look-back time as a function of redshift, or alternatively, age of the universe as a function of redshift, measured in units of the Hubble time for a variety of different models. They all behave qualitatively in similar fashion, but the curves are separated. So this is what will lead us into cosmological tests. We're trying to determine which R of t curve we live on. This is really done by measuring redshifts and some form of distance. But take these curves and pinch them together when the slope is the same. In other words, when they have the same Hubble constant. Well, then the intercept on the time axis will be different for different curves. Cosmological models with high densities and or zero cosmological constant will tend to have smaller distances, smaller look-back times, and smaller volume than models with lower densities and positive cosmological constant. Thus, if you pinch these curves at the same value of Hubble constant, which is the same slope, and see where the intercepts are on the time axis, the lower density or positive cosmological constant models will tend to be larger and of longer duration. So the objects in lower density models or models with positive cosmological constant would appear smaller and fainter than they would in the, say, models with high density and no cosmological constant. So next we will start looking into measuring the scale of the universe, or the Hubble constant.